A potential divider and potentiometer are the application parts of DC circuit. So this one also is important to know. Okay, so what we'll just tell you first is this. A potential divider is just used to supply variable PD at the output of a circuit. When you have a circuit and you want to get something like changing voltage out of it, you will use what we call a potential divider. A potential divider circuit usually must have two resistors, at least two resistors that are connected in series, like what you're seeing over here. You need to have two different at least two resistors connected in series. Once you have that, you will be able to get any fraction of the input PD just by varying one of the resistances. Okay, so in your example right now, you want to get the output PD from this resistor. Okay, input PD right now is provided by your battery. Your output PD right now is provided by your RV by varying the resistances there. What we'll tell you is that if your variable resistance is 0, your output PD is 0. If your variable resistance is max, then you have maximum output PD. Okay, but what you're interested to know is how to calculate out the PD. So this is where you need to know, or you need to use one particular equation called the potential divider equation. This is what we call your potential divider equation. Now, potential divider equation, the derivation is not required to be known. You just need to know the general form of your potential divider equation and when are you supposed to use it. So if I were to, this one here is just showing you the derivation of the potential divider equation. So now, let's just say for this circuit right now, I want to apply Kirchhoff's second law for this loop. V in is equals to VR plus V out. Okay, I get this. And then notice also that because this is connected in series, the same current flows through, right? The same current flows through them. So V in is actually equals to IR plus IRV. Okay, this is the first equation. Now, if I just single out this portion here, I can say that V out is actually the current through it multiplied with the variable resistance. This is your second equation. If you divide 2 over 1, V out over V1 will be IRV over IR plus RV. So the R's will cancel off, giving you this one. V out is RV over R1 plus RV plus V in. Okay, another typo mistake here. Just get rid of the R. Again, I will just correct it later for you, okay? Right, so this is the potential divider equation. Now, bear in mind that potential divider equation, this one, you can only use it if the same current is flowing through all the resistances in the equation. You see RV and R are having exactly the same current flowing through them. The potential divider equation can only be used if you have same current flowing through them. You cannot use them if you suddenly have different currents in the different resistors being considered. Okay, I will show you that one later. Okay, so from here, you can see that your potential divider equation is used to find the proportion of total PD that is taken up by a resistor in a network of resistors. Okay, you are trying to find how much of a fraction of the total PD is it, just by looking at the fraction of the resistances. In other words, okay. Now, if you look at the second diagram here, since the same current is actually flowing through R1 and R2, I can apply the potential divider equation straight away to them. This one will be I, this one will be I like this. I. Okay, so this one here, I can see that for R1 and R2, same current flows through them. I can actually use the potential divider equation straight away for either one, in order to find out what is V1, in order to find out what is V2. So if I want to find V1, it will just be R1 over R1 plus R2 times V8. Or V2 will just be R2 over R1 plus R2 times V8. Okay, this is for this part. Okay, now there will be some questions that you encounter as you do your partial questions that ask you to find potential at a point. All right, so in the lesson last week, I mentioned that EMF and PD are just simply differences in potential between 2 points. One is gaining electrical energy, causing increase in potential. One is losing electrical energy, causing decrease in potential. Okay. And then after that, I also mentioned that potential in itself is actually just value at a certain point. It won't change unless your charge passes through a battery or a resistor. Okay. So sometimes your questions may ask you to find potential at a particular point. So let's just say in your circuit right now, they're asking you to find potential at point P in the circuit. All right. The point P is actually here. I think I should use a green color here. The point P is here. They want you to find the potential here. So usually when you want to find the potential there, we will tell you it's often easier to find the PD from the zero potential side of the circuit. Okay, what do I mean by that is this. If I tell you that your EMF is again 12 volts, and then I will tell you that your PD across R2 is 4 volts, and your PD across R1 is 4 volts. This one is PD, this one is PD, and this one is EMF. The potential here, it'll be easier to find the PD from this side. Okay, now let me just draw for you the potentials, variation of potentials. If you're talking about from here going all the way to here, this one will be 12 volts potential. And then after that, from here to here will be 4 volts potential. Here to here will be 0 volts potential. Okay, so this one was what we mean by the potentials across the circuit. All right, it won't change unless your charge passes through a battery or through a resistor. So what we'll tell you now is that if let's just say you're only given the value of the EMF, and then you have a choice of either finding the PD across R1 or the PD across R2, which one is easier for you to find out the value of potential 4 volts here? So usually what we'll tell you is that it will be much easier if you find out the potential from the zero side of the circuit, potential difference from the zero side of the circuit. The zero side of the circuit is referring to this one. Okay, this part is 0, right? So if you want to find the potential here, it's easier to find the PD across here. Because if let's just say that this is 0, to find the potential here, you just need to know the difference in the PD across here. It will just be 0 plus 4 volts giving you potential 4 volts. Okay, that's what this statement here means. When you want to find potential at a point, just find the PD from the 0 potential side of the circuit. The potential at that point is equal to the PD at that point itself. Okay, which is this one. No further calculation is required. But if let's just say you don't want to find from this side, you want to find the PD from this side instead, you're going to get 8 volts. But is the 8 volts here going to be the potential at point P? It isn't, right? What you're going to have to do is that you need to take 12 volts minus of 8 volts to get 4 volts. Right? So VP here will be your VE minus V1. Notice that there's an additional calculation required here. Okay. So this one here is just something for you to know when it comes to calculating potential. When you find potential at point, just find from the 0, find the PD from the 0 potential side. Okay. The PD that you get is already going to be the potential itself because you're starting from 0. 0 plus with the difference or the PD will give you the value of potential at that point itself. You find at any other point, you notice that you have to subtract. You have to do some further calculation. Okay, so that's what I just want to highlight. Okay, now the last part about potential divider is this. Just like I mentioned to you, your potential divider equation can only be used if you have same current flowing through your resistances. Your potential divider equation cannot be used if the resistors have a parallel connection. Okay, meaning to say, if you have parallel connection, you don't have same current. Okay, the one main thing I mentioned is you can only use this if you have same current. Okay, if you don't have same current, you cannot use potential divider equation directly. This usually happens when you have a parallel connection. Okay, so let's just say if I give you this circuit here right now to illustrate what I mean, notice that for this circuit, I can have current I. It will flow through here. It will hit this junction, and then it will split up. Okay, now maybe I see this I1. It hits the junction, it splits out, it becomes I2, it becomes I3. So notice that all three of these resistors do not have the same current. So when it comes to finding the PD across those resistors, it's not as straightforward as saying V1 will be equals to R1 over R1 plus R2, okay, times V in. Neither can you say that V3 is going to be R3 over R1 plus R3 times V in. This one you cannot do so, okay? Mainly because in the first place, your potential divider equation was derived based on the assumption that they have same current, which eventually cancel off. So you try to use it here to find the PD, V1 and V3, you are never going to get the correct answer. This is wrong, okay? So you cannot do this because the current is not the same, okay? Not valid because same current is not flowing through the resistances. But what you can do later on in order to find out the PD is this. What you should do is that you should simplify this portion here, the parallel connection here, into a single equivalent resistor, R parallel. When you do so, you will notice that it's actually going to be the same current flowing throughout both of these resistors. Now, in cases like this, when you want to find out what is V1, you can use your potential divider equation straight. Here you can say that V1 is equals to R1 over R1 plus R parallel times V in. This one no issues because same current is flowing through both of them. This one is correct. Likewise, you can also use this to find VP, the V parallel. Okay, where we tell you it is R parallel over R parallel plus R1 times V in. Okay, there's another typo error here, parallel. Okay, so this one you can find VP, all right? Again, is correct because you have same current flowing through. Now, as from here, then that you can say that the voltage across this parallel connection here, okay, the voltage across this parallel connection here is going to be the same as V2 and V3 from here. Okay, here you use potential divider equation to find VP. Whatever you're getting here will be the same as the PD in the parallel connection. This one comes from this part of your notes. Remember this one under page 6 of your notes? Page 6 of your notes. I mentioned that when you simplify a parallel resistance, the PD across the parallel resistance is actually the PD across your resistors itself that were in parallel. So this, by doing it this way, you can find the PD. All right. So far so good with this. Okay, so this is the important thing to know for potential divider. Okay, then we go to the last one, potential meter. This is the thing that most people have problems with. The questions don't come out that often, but I find this is the one that most people have problems with. Okay, so this one I'll try to go a bit slower. Okay, now, what is a potentiometer? A potentiometer is kind of like a voltmeter, all right? You can just think of a potentiometer as something that looks like, it acts like a voltmeter, all right? Why do we need a potentiometer to act as a voltmeter? The reasoning is because when you have an analog voltmeter, the accuracy with which PD can be measured is limited. What do we mean by that is this. If I give you a circuit like this right now, I tell you that this one here has 10 ohms, and then this one here has say 30 ohms, and you have a current of say 2 ampere that is flowing through this circuit. Okay, you have a current of 2 ampere that's flowing through this circuit. Right, let's just say that this is R1, this is R2. Now the voltage R1 here will be equals to I times the resistance, which is 2 times 10, giving you 20 volts, right? Okay, this is by right what you should have for the PD across here. Okay, but let's just say right now, rather than calculating out the value, you want to measure it using a voltmeter. When you try to measure it using a voltmeter, what you would do is that for that same circuit, where you have the same 10 ohms, and the same 30 ohms, you connect a voltmeter across it in order to be able to measure the PD. Okay, this is what you would do to calculate to measure the PD across the resistor. Okay. Now, the moment you go and connect a voltmeter in parallel with the component that you're trying to measure, it will actually draw some current from the circuit and change the behavior of the circuit to which is connected. Okay, so voltage measurement is inaccurate already. Okay, why do I say this? You see, if your voltmeter can draw some current, what will happen is this. Your current, maybe it is 2 amps, still same 2 amps as before, just to illustrate to you the example. It's the same 2 amps as before. It flows, but then after that, it will reach a junction, which is this part here. Your voltmeter here can now allow current to flow. Okay, so what happens here according to Kirchhoff's first law is that once this current of 2 amps hits this junction, it will tend to split up. So your current of 2 amps has actually split out at this junction. It could be that maybe you have 1.8 amps here, and then this one here you have 0.2 amps. But the fact is that you putting the voltmeter here has actually changed the circuit. You are actually changing the actual current that is actually flowing through your resistor. So your voltage measurement here will be affected. What do I mean by that is that if you see this one here, your resistance is still 10 ohms, but now your current is 1.8 ohms, 1.8 amps, sorry. If you try to calculate out the voltage, the current multiplied with the the current multiplied out with the resistance, you're gonna get the value as 18 volts. You see, originally you're supposed to get 20 volts, but then once you go and connect your voltmeter here, because it's drawing current away, it already changes the behavior of the circuit. It will cause your voltmeter measurement to be inaccurate. You're getting a different value now. All right. So that's the reason in the first place why we mentioned to you an ideal voltmeter should be drawing no current so that the measurement of voltage is accurate in the first place. Okay, so to overcome problems like this, where the act of you trying to measure something causes the thing to be inaccurate, that's why we have the concept of potentiometer. Okay, now a potentiometer is actually a type of potential divider that can be used as a very accurate meter. The basic circuit is as shown below. Okay, so just bear this in mind. I'm going to clear off the drawing and then scroll downwards. So let me clear off everything. Okay, so your basic circuit of potentiometer is just this. Your potentiometer is meant to measure voltages of something. So right now, when we say potentiometer, this thing here that I highlight in pink is your potentiometer. The PD that you want to measure, the voltage of the component you want to measure, is this blue colored thing here. Okay, so we don't bother about this one first. We bother about the potentiometer itself, which is the thing that I've highlighted in pink here. Okay, so there are a few characteristics of your potentiometer. Number one, you will always have a driving cell that will drive a current through your uniform resistance wire. You will always have a cell and you will always have some sort of resistance wire. Okay, the resistance wire would have some sort of EMF E, and it will cause current to flow through your resistance wire. Okay, so from here, what we'll tell you is that according to Kirchhoff's second law, the PD across the resistance wire, okay, the wire here is talking about resistance wire. I'm not talking about these wires here. I'm not talking about connecting wires. I'm talking about the resistance wire. Okay, so be very clear on that. The resistance wire. According to Kirchhoff's second law, the PD across the resistance wire will be equals to E. Okay, so here you will have a source of PD, okay, across your wire because it is resistance. So according to Kirchhoff's second law, the PD across your wire will just be equals to E. Okay, so this much you understand. Now, from this uniform wire, the resistance is going to be directly proportional to length. This is from what you learned under the previous chapter, where we tell you that resistance is rho L over A. Okay. But since right now your rho and A are constant, R is proportional to L. Your resistance is proportional to length. Okay. Rho here is your resistivity. It depends on your material. Your wire here is made from the same material throughout. Obviously, resistivity will not change. Your wire is uniform, meaning to say the cross-sectional area is uniform, so area does not change. So rho and A constant, R is proportional to L. Okay, so this one is the first relation. The second thing you will need to know is that V is equals to IR. Now, I apply V equals to IR for this entire portion. I apply V equals to IR for this entire portion. Now notice that for this entire portion, the same current I is flowing through them. So I can say that same current I flows through the resistance wire, therefore V is proportional to R. This is the second relation. Now, if you combine relation 1 and relation 2 together, you're going to get the conclusion that PD across the wire is actually proportional to the length. Okay. If anything you need to know about potentiometer, the relation, this is the most important one. V is proportional to the length. The PD across your wire will be proportional to the length. Okay. Whatever I just did before was something like a derivation to show you why. Okay. It's not required in your syllabus, but I just show you anyway. Okay. So from here, you understood that voltage is proportional to your length. This would mean this. This would mean that the full length AB of your wire is now corresponding to a total PD of E. Okay, full length of your wire is this. Your A is here, your B is here. The full length of your wire corresponds to a total PD of E. For any length that is lesser than the full length, you will only have a fraction of the value. Okay. So if say right now, your resistance wire is this, and I tell you that this one is 100 centimeter, and maybe for example, I give you some values. Your EMF is 12 volts. Your EMF is 12 volts. This one, your PD would also be 12 volts. But if let's just say your length is slightly less than the full length right now, maybe you're talking about 50 centimeter, your PD would across it would be correspondingly less. Here your PD probably would be half of the original since your length is half, right? So this one will be 6 volts. That's what we mean by that. Okay, you will right now you're going to get a fraction of your EMF E. Okay, so far so good with this. Okay, then I move down to the bottom part. Right, this is where things get a bit complicated. Okay, now if you look at your diagram, we tell you that point C get rid of everything here. Now you look at your diagram, there is a point C, right? You have point A, point B, point C. Okay, now point C is a movable contact on the wire that is made by a sliding jockey connected to a galvanometer so that the PD across AC can be varied. Okay. Now you see your movable contact C is made by a jockey. A jockey looks like a metal pen, that's all, that's connected to a galvanometer. A galvanometer is something like an ammeter. It's something like an ammeter. But the only difference here is that the galvanometer tends to have the 0 at the center, so that it can deflect either left or right. Your normal ammeter tends to have your 0 right at the side. Okay, that's what the galvanometer actually is. Okay, so that one is just some extra knowledge for you. Just think of a galvanometer as just equivalent to an ammeter. All right, so your sliding jockey is what determines your position C. So when you shift your C around, it determines your length L. So just now you know that this length L determines the PD across. So if you go and change your length by sliding the jockey along the length of the wire, you're going to vary the PD across the length of the wire. You're going to be varying the length across AC itself. Okay, so that one is what you need to know. The length vary, the PD across the wire will vary. Okay, so now we go to the part where we talk about the PD to be measured. Just now I told you that your potential meter is this pink colored section here. When you want to measure a PD or whatsoever, it is this portion here, right? So I'll say right now you have a PDV that is to be measured. Okay, you connect it to points D and E in the circuit, right? You connect it to points D and E in the circuit, ensuring that the more positive potential is connected to D and the less positive potential is connected to E. What we mean by that is that if let's say your PD here, this side is more positive, this side is more negative, make sure that this positive is connected to this positive, this negative is connected to this negative. Okay, look at the terminals of your driving cell. This one here is positive, right? When you want to connect your PD to be measured, make sure your positive aligns with the positive here. And then likewise, make sure your negative aligns with the negative here. Okay, that's what we mean by that. Okay, now once you connect your PD to be measured, what you're supposed to do is this. you slide the position of the sliding jockey until your galvanometer reading reaches 0. Your galvanometer is like an ammeter. You slide your jockey left and right until your galvanometer reading is 0. Okay, so at this point here, we will say that your potentiometer is balanced and the length AC that you have is going to be the balance length. Okay, so the main goal of any potentiometer, you try to slide it until your galvanometer reading is 0. Okay, until your galvanometer reading is 0, and whatever the length you have is your balance length. Okay, from here you will get a few things. Under the previous chapter, I mentioned that current can only flow when there are differences in potential between 2 points. So when there's no current flowing through the galvanometer right now, it means that potentials at A and D are equal, potentials at C and E are equal. Okay, to give you an idea of what I mean by that, we say that V for potentials now, we say the potentials VA is equals to VD, VC is equals to VE. Okay, so it could be that maybe I tell you that this one is 12 volts. All right, and then after that, this point here is 12 volts potential. This point here is also having 12 volts potential. And then if I tell you that this point here has maybe 4 volts potential, this point here also has 4 volts potential. Okay, so the key takeout point here was just this. If your ammeter, if your galvanometer reading here was equal to 0, that means no current flows. Okay, current will only flow when you have differences in potential. But the fact is that your galvanometer reading here is 0, means that there's no difference in potential between these 2 points. That's why we say to you, VC and VE have same potential. And then likewise, due to implications of Kirchhoff's first law, it will also mean that VA, potential at A and potential at D are the same. Okay, that is what this statement means, right? So potentials AD, same, potential CE, same. Now, it's because of this that you eventually be able to see that the difference in potential between this one, between D and E, would be the same as the difference in potential between A and C. Okay, because you see potential here is the same, potential here is the same, therefore the difference in potential here would be the same as the difference in potential here. Okay, so just understand that part. That's why here we will say to you the PD across AC will be equals to the PD across DE, which coincidentally is the PD that you want to measure. Okay, which is the PD that you want to measure, which is V here. All right, that's the key takeoff point here. At your balance length, the PD across your wire is equals to the PD that you want to measure. All right, so to put it simply, just think of it as this. When it comes to the potentiometer, once your galvanometer reading shows a 0 deflection, the PD measured is always equals to the PD across your balance length. That is what it means. So let's just say this one now is at 0. This one here is your balance length. The PD across this balance length will be equal to the PD that you're trying to measure. That is the main thing here. Okay, so when it comes to this one, you can actually use other different PD or EMF connected to D and E to produce different balance lengths. And then from there, once you have the balance length, you can actually find out the PD value that is being measured. Okay, what do we mean by that is this. Let's just say, for example, I tell you that the resistance wire had the length of 100 centimeter and the total PD across it was 12 volts because EMF just now was 12 volts. Okay, so this one was before I connect the potential, before I connect the PD to be measured. Once I want to measure the PD, I go and slide the jockey around until my galvanometer reading reaches 0. And I found out that the balance length is 55 centimeter. So I want to find the PD across that balance length. When I am able to find the PD across that balance length, it will be equal to the PD that I want to measure. This is the most important thing for a potentiometer. 0 reading across your galvanometer, the PD across your balance length is the PD of whatever you want to measure. Okay, so you're trying to find that PD across your balance length right now by using this relation, because V is proportional to L. Therefore, V2 over V1 is L2 over L1. So if let's just say V2 over V1, L2 over L1, V2 is the voltage I want to measure right now. V1, I already know the first case is 12 volts for a length of 100 centimeter. For the voltage I want to measure, the length is 55. So I get this. So the PD that I want to measure is going to be 6.6 volts. Okay, this is how I would do the calculation. All right. Okay, now some other things I should mention to you. At balance point, no current is actually being drawn from the circuit whose PD is being measured. Okay, so in your diagram here, you just see that this one is the something where I say PD is being measured, right? The PD being measured, the full diagram could look like this. Okay, this entire thing here is your potentiometer. Okay, the PD to be measured is this thing here, and it's part of a main circuit like this. Okay, so now when you go and connect a potentiometer and then you go and change your slightly jockey around until your galvanometer reading reaches 0, no current will be drawn from the circuit whose PD is being measured, which is this one here. Now, there's a top circuit here and there's a bottom circuit here. Both can have current flowing, but the currents do not mix with each other. They do not cross with each other. You see this one here, the potentiometer has its own current, I. The bottom circuit here also has its own current, which is I. Okay, now let's just say that this is I top, this is I bottom. Okay, current will still flow in the top circuit with potentiometer, and also the bottom circuit with the component whose PD is being measured, but their currents do not cross. So the circuit whose PD is being measured is not being altered. Remember just now I told you that one of the things about connecting an analog voltmeter was that it draws current away from the circuit whose PD is trying to be whose PD is being measured. The moment your voltmeter draws current away, it causes the voltage to be inaccurate. So that was the problem there. That's why you wanted to use a potentiometer here. So your potentiometer here, by right, it will never draw current away from the circuit that's being measured. So this one here is your potentiometer. This is the circuit whose PD is being measured. Okay, so that's why we will say that your voltage reading is going to be accurate. Okay, so another thing I should add here was that the part where you connect the positive and positive terminals together, negative and negative terminals together, under this part, just now I said, well, where was it? Yeah, when a PDB is to be measured, connected to points D and E in the circuit, make sure positive potential is connected to D and the less positive potential is to E. And there's a very specific way to connect your potentiometers with the circuit. Remember just now, this one here is your driving cell, this is positive, this is negative. Whatever you try to connect to your potentiometer, make sure that the positive and negative match. You see this one here for the circuit whose PD is being measured, positive must line up with the positive. Negative must line up with negative. This is the only way your potentiometer can work. If you suddenly do it like this, negative, positive, this will not work. Okay, I believe there's an MCQ question or two that tests you on this knowledge. So please be mindful of that. All right. Okay, so this one is just talking about measuring PD of a component. There could also be some other examples where we tell you the potentiometer can also be used to measure the true EMF of a cell. Okay. Now, even if your cell has internal resistance, it does not affect the balance line. Okay. What I mean by that is that, say for example, this one was 12 volts. This one is say maybe 4.5 volts. When you go and change your sliding jockey position, this one reads 0. At balance length, the PD across this wire will be equals to 4.5 volts. Let's just say right now maybe it is 35 centimeter. Okay. Now, even if your cell has internal resistance like the one here, it won't affect your balance length. If your EMF here is 4.5 volts, you're still gonna get the same 4.5 volts here at the same length. The reasoning is because what we'll tell you here is that in this arrangement, there's no current flow through the test cell. Thus, there will be no PD across the internal resistance, hence no voltage loss to consider. Right? Because if you look at the current flow here, there is only current flow at the top part of the circuit. Current will flow like this only. There's no current flow at the bottom part of the circuit. Okay, so this one, no current. This one also no current. So even you take a battery with internal resistance and you connect it to potentiometer, what you're measuring is actually just the EMF. There's no voltage loss since no current flows through it. Okay, you're going to get back exactly the same balance length. Okay, right. So another thing I probably should mention, yeah, basically just not this one. I can also do for you the same example. If this one has a PD of 6.6 volts, this balance length would be 55 centimeter, representing a PD of 6.6 volts. If you're talking about it at 100 centimeter, it had a PD of 12 volts. Okay, so the key thing is to remember, once galvanometer reading is 0, the PD across your balance length will be equals to the PD across whatever you're trying to measure. Okay, that's the main thing here, key take-off point here. Okay, right. Okay, I went past the time already. Do you want me to explain the last part? You probably just take maybe less than 5 minutes. Should I explain it to you to close out the potentiometer part while the thing is still fresh? Okay, right. Okay, so another thing that could be that the question can sometimes ask you also is this, for potentiometer, is this. Let's just say right now I have the same circuit as before, but this time I connect a variable resistor. Okay, you see this circuit here is the same as the circuit before, but there's some addition that I do that was made to the circuit. What we say here was that we go and add a variable resistor here. Okay, so if before I told you that your EMF here might be say 12 volts, your whole length here would be equals to EMF, the PD across your entire length here will be equals to E, will be equals to 12 volts. Okay, that was one of the key understanding for this part. Now, the moment you go and add another variable resistance to your circuit, what will tell you here is that your EMF will be divided between the resistor and the resistance wire. So if before this, I told you that your EMF here, E, was 12 volts, this entire length is no longer going to be 12 volts because now you have another resistor inside here, right? If you were to try and apply Kirchhoff's second law through this entire loop, your total PD, your total EMF will be split between these two. So it could be that maybe you're getting 8 volts here and then 4 volts here. Okay, now maybe I go and change. I've been using 8 and 4 a lot. Maybe I change it later. It could be that maybe here you're having 10 volts and then 2 volts. Okay. So your PD will be divided. Your resistance wire is not going to have as big of a PD across the full length anymore. Now, when you want to find the actual PD across the wire, sometimes you could use your potential divider equation. Remember just now, this one here, I told you that when you use your potentiometer, by right, current will never go down to the bottom circuit. It will be confined within this loop only. So if you wanted to find the PD across the wire, you want to find the PD across the wire, you could easily just use potential divider equation where we tell you VAB is the resistance AB divided by resistance AB plus resistance of the variable resistor times with E itself. Okay, and then now what we can say here is, let's assume the same PD is being measured as before. Okay, the PD being measured, I can say maybe is 6.6 volts. Just now the EMF was 12 volts. I'm following the values that you have here. Okay, I'm following the values that you have here. All right. Say just now the EMF that you want to measure has a value of 6.6 volts. Okay. Right. It has a value of 6.6 volts. Say for example, right now. Okay. So it's a value of 6.6 volts. The PD to be measured is 6.6 volts. Right now, when I go and add my variable resistor inside, this total PD is divided between this and this. So say, for example, right now, I say that for this whole full length of wire, 100 centimeter is now 10 volts. Okay, 100 centimeter is 10 volts. This one is 2 volts. Okay, so now when I increase the resistance of my variable resistor, I know the PD across variable resistor will increase while PD across the wire will decrease, like what you see here right now. Now, when I have the variable resistor inside, notice that before this, without the variable resistor, it was 12 volts. But now with the variable resistor inside, the PD across my wire has now dropped to 10 volts. Okay, so I can say that the PD per unit length across AB has decreased. Okay, to obtain the same measured PD as before across the resistance wire, my balance length would need to be longer. Put it this way, if I just give you this case now, what you understand by now is that my PD being measured is 6.6 volts. I need to move the movable jockey left and right until my galvanometer reading is 0. When my galvanometer reading is 0, the PD across the wire would be 6.6 volts. That was the main understanding behind the concept of potentiometer. But right now, that same resistance wire of 100 centimeter, the total PD across it is just 10 volts. It is no longer 12 volts. So where do you suppose I need to move my jockey to? Should I move it towards the right or left in order to get the same PD of 6.6 volts? The key thing is to understand that your PD per unit length has decreased. If just now before, I told you that 100 centimeter is representative of 12 volts, that means I will get, where's my calculator? That means I will get 12 divided by 100, I will get 0.12 volts per centimeter. But now after I go and add a variable resistor inside to reduce the PD across my wire, 100 centimeter is now 10 volts. So my PD per unit length is now 0.10 volts. So now my PD per unit length has decreased. I still need to get 6.6 volts. Wouldn't this tell you I actually need to get a longer length now in order to get back the same 6.6? That's why here we tell you to obtain the same measured PD, your balance length will need to be longer. You need to move your contact closer towards the end, towards NB, so that your galvanometer reading reads back to 0. Okay, that is what we want to do here. Yeah, okay. The values, yeah, go and draw the values at the top diagram. I should have just drawn the values below here for a diagram. Okay, so that was the understanding behind this. No? So let me just quickly go and label the diagram for you. E is 12 volts. This one is 2 volts. This one right across is 10 volts. Okay, so my PD being measured is 6.6 volts. Okay, this one is 100 volts for 100 centimeter. So this one here at 55 centimeter, this one is no longer 6.6 volts. This one is no longer balanced. Okay, so what you do is that you need to shift your jockey further apart. Okay, this is 6.6 volts. This one E is 12 volts. This is 2 volts. You need to shift your jockey along to maybe a different length. Okay, so what could be the length? Okay, now what length do you think I should have? For 6.6 volt, the length required is 6.6 divided by 0.1. I'll get 66 centimeter. Okay. 6.6 divided by 66 centimeter. So this one now will be 66 centimeter, corresponding to 6.6 volts. Okay. Balance length is longer. Okay, so this one here, the old one, at this length, 55 centimeter, the arrow here is no longer 6.6. It's no longer balanced. Okay, because PD per unit length has decreased. Okay, right. The main thing is always go and change the galvanometer, go and move the jockey around until your galvanometer reading is 0. Once your galvanometer reading is 0, whatever PD you have at the top of your resistance wire will be the PD or EMF or whatever you have at the bottom. Okay, so look at the last page. There are some additional things under DC circuit that I ought to mention to you guys. Okay, in the last session, we went through the concept of potential meter, which in general looks something like this. Okay, But sometimes when you do your question, you might notice that there is some mention of a potential meter also, but it doesn't look like the potential meter that you learned last week. Instead, it looks like this. It has the symbol of a fixed resistor with some sort of arrow that is on the fixed resistor itself. Okay, so this potential meter that you're looking at is actually some sort of variable resistor. Okay, it is not like the potentiometer that you learned in the last lesson. Okay, the circuit symbol looks like this. Eventually, when you do your partial questions, you will see this little symbol here. Okay, so what we'll tell you here is that that arrow that you see, you can either shift it towards the left or you can either shift it towards the right. When you shift that arrow towards the left or right, it actually varies the resistance of that potentiometer. Okay, so its main purpose is mainly just to vary resistance. It's a bit different than the potentiometer that you've learned last week, where it is used to measure voltage. It acts like a voltmeter. So below the page, you will see that there are some diagrams here showing you the potentiometer. Okay, now the potentiometer that I was talking about, if you look at the left hand side of the diagram, looks like this one. Okay. So I mentioned to you that the arrow can be shifted around so as to vary the resistance of your circuit or resistance of your potentiometer. Now, in general, if let's say your arrow is say right at this edge here of your potentiometer, it is actually akin to you connecting to before the resistance itself. But on the other hand, if you see that your arrow is connected right at this other end here, it is akin to you connecting to right after the potentiometer or after the resistor. Okay. But if you look at the last diagram, if you see that it's connected, say somewhere in the middle of your resistor, it actually has the effect of kind of splitting up the resistance. If I say this one is actually exactly halfway, if I say this one is exactly midway of your potentiometer, you can think of the resistance here as having been split into two. Okay. So an equivalent circuit could be that you are actually connecting like this. Let me change the color. An equivalent circuit could be that you're actually connecting like this, right between the two, right in the middle. You're actually connecting right in the middle of the resistance arc, so that there's R2 on the left side and R2 on the right side. Okay, this is potentiometer of another kind. Okay. Okay, then after that, the last thing I should mention to you is short circuit. Okay, now short circuit in your syllabus is something like this. It usually occurs when there's a path of zero resistance for current to flow at a junction of an electrical circuit. When you have short circuit, you must have zero resistance in a particular path. So in such cases, all the current will flow through this path without splitting up at the junction. So if let's say I give you an example diagram like this right now, where you see that there are two resistors and an open switch, if you were to look at this diagram itself, current, there's actually a closed circuit here. Okay, your closed circuit is actually this blue colored line here. Okay, this bottom part here is open, so it's not considered as a closed circuit. So only the top part is considered as a closed circuit. So here, what will happen is that your current will actually flow like this. Then it reaches this junction. Because this one is a open circuit, nothing goes inside. It will just continue flowing like this. This is how a normal circuit would look like. But then, yeah, so before I go any further, when your current flows like this here, because these two resistors are equal resistance, what you could also say is that if this one is E, by right, these two will be equal to E also, according to Kirchhoff's second law. All right. But then because they're of equal resistance, this one will take E over 2. This one will take E over 2. This is the PD across them. So that's why I mentioned here, the current flows through the resistor and the EMF is divided equally between the two resistors R because they have the same resistance. Okay. Now, what happens if you were to close the switch? If you were to close the switch, let me just go down. Let me clear off the thing. If you were to close the switch like what you see here, you now have what we call short circuit. Okay. You see, previously, with the switch open, this one was my circuit that I consider, right? This is the closed loop that I consider. But right now, once you close the switch here, the closed loop that you need to consider is actually this one. This is the loop that you actually need to consider. You will not consider this one. Okay, wait, let me just rewrite this. You won't actually consider this, right? The reasoning is because this part here, at this junction, by right at this junction, you know that current ought to be able to flow in this direction as well as in this direction. But there's something special about the path at the bottom part. This path here is actually considered to be your short circuit. Okay, let me rewrite this. This part here is considered to be your short circuit, right? Because here, this entire path here is considered to be your short circuit because it has zero resistance. Okay, this pink colored path that I've highlighted here is considered to be your short circuit path because it has zero resistance. Okay, so the key thing to identifying whether you have a short circuit or not is that look at your junction sometimes. Look at your junction when current is supposed to split off. Look at the junction where current is supposed to split off. And then after that, see whether there's any path where there's zero resistance. If there's zero resistance, that one is already considered to be your short circuit. So what will happen then is that no current will flow through the other path. Current will only flow through all the current will flow through the short circuit. Okay. So if I were to draw out the current flow here, it goes like this, it goes like this. So this junction got short circuit indicated by the pink colored line here. All your current just flows through this path. It doesn't go through the top path. It won't go through the top path. It will just go through the bottom path because that is a path of short circuit with zero resistance. So your current just goes like that, and then it continues going up, up until it goes back. Okay, so this one is what we mean by short circuit. All the current will bypass the second resistor to flow back to the battery. And because there's no current through the second resistor, there is no PD across it. Okay, your resistor, the first resistor here, will actually take out the entire PD following Kirchhoff's second law. Because if you look at the blue colored line here, the blue colored line that I've just highlighted, this one is your EMF. This is your only PD. So if this one was E, this one obviously would be E also. Okay, so this is what short circuit actually means.